Okay, good morning, everyone. Thank you all for being here. Thank you, Victor, for the introduction. Yes, as Victor said, I'm leaving, so I'm a bit sad because of this, but I'm happy for all the amazing people I met during this time here. I'm particularly excited today for presenting this work. So yeah, it's the second pillar of this kind of work I've been doing here, connecting machine learning with physics, or trying to connect it. If you have any questions, please interrupt. Feel free to do so. Okay, so let me give you some context and the field I'm interested in and the research I have been doing here at IFISC. It concerns the physics of thought. Okay, so on one hand, we have the brain, one of the most complex systems in the universe, studied by neuroscientists, medical doctors, psychologists, philosophers for centuries, studying the emerging properties that the system have. And now we also have the neural networks, right? So these artificial brains that the engineers have scaled up to a level of complexity similar, at least in size, to the human brain. So there are these emergent phenomena, and it's the role of theoretical physics and the physics of complex systems to understand actually the foundations of these mechanisms, regardless of the physical substrate in which they operate, either digital, silicon, or carbon, organic, or whatever. And also physics has taught us the useful role of minimal models. Okay, so trying to get the minimal explanations for this phenomena. It's very trendy. This just mentioned the Boltzmann medal that is going to be awarded to Kuramoto and Kardar, or the Nobel Prize for Hopfield for the minimal model of memory, right? So we have recognition for the minimal model of synchronization, minimal model of memory, and so on. And I guess I would like to believe that this philosophy is shared here in this institute by a lot of people. There have been many interesting works here. For instance, regarding the foundations of quantum mechanics, foundations of quantum machine learning. We have here experts on these models for decision making, like Boter model. We have interesting coming theses like the one of Pedro with Lucas, or the thesis of Mirko Ullmann about conceptors and ideas of neuromorphic computing. Well, I think this philosophy is shared. Let me just illustrate this idea with another example, the one that Victor mentioned before, about this first pillar I did in collaboration with Lucas. It's published in peer research for those who are interested, the effective theory of collective deep learning. The idea is very simple. I will not spend a lot of time just saying that we study collections of brains that interact, right? So this happens in the natural realm, where in a society or here in the seminar, each of us has its own information. We share it with the others, so we learn from each other. This also happens in the digital realm. So engineers put these neural networks and train on different data, and they share the parameters, and something emerges from there, and they are able to learn from each other. So what I did here was just for a wide class of dynamics for this kind of systems to show that they can be reduced to a much simpler system of very low dimensional dynamics that is nothing more than a Ginzburg-Landau with a quench disorder. So basically you can see these collections of brains as interacting spins, right? So we can use this minimal theory again to make some predictions, and that's what we did. And you can predict some phase transitions in the genotype, so in the weights of the model as you increase the coupling, or phase transitions in the collective learning that occur later, for instance, as the brains are more complex. Some cool stuff, or for instance, the microscopic path. So predicting who is learning from who and at which order, depending on the data they have, which is like the disorder. Okay, so this is cool, but I'm not talking about this today. This work, I think it maybe came too early, because yeah, it's like the minimal model of collective learning for natural systems or digital, but it's something like happening at the global scale. So for the collections of brain. But there is a more urgent or perhaps interesting question that to solve at the local level. So it's not very well understood how learning happens at the local level, so for one single brain. And that's what I'm going to try to explain today. Okay, so that's the situation we all know. We are merged in this revolution of AI, and we have all witnessed the eruption of large language models, like the ChatGPT, Gemini, DeepSeek, Claude, blah, blah, and so on, so on. They will change a lot of fields, from research to society to economy and so on. Let me give you an example that is not mine, but made by Andrej Karpathy, which is one of the heroes of this AI revolution. Very interesting guy to follow. And he talks about software. So just this simple example. So before we had software 1.0, the usual code, right? So we have codes, we can write them in Python, in C++. They are text files that we send to the compiler and produce something. This has changed. Already with deep learning, we had software 2.0. The programs are not anymore the text files, but the weights of the neural networks. And people, so here there is the GitHub, so showing the ecosystem of different codes and how they relate to each other. And you can go to Hugging Face, which is like the same idea, but for models, and you see like another ecosystem that is growing. People using the programs from other people to build new programs, but these programs are weights. And this paradigm also changed. Now we are in the 3.0, which the programs are the prompts themselves, because these neural networks, like transformers and so on, become themselves programmable. So now the programs are encoded in the prompts that you send to the neural network to produce a code. So it's kind of crazy. Things have changed a lot quite fast. And everything comes from a single idea, a very simple and a stupid recipe. That is this idea of pre-training at scale. What this means: 4 ingredients. First ingredient, you have to invent the transformer, okay? People from Google did that. It's a big neural network just that handles very well sequences of text. So it's an autoregressive model that has this attention mechanism, whatever, quite highly cited also. Second ingredient, you need data. What these people use, massive corpus of human-generated data. Basically, the whole observable internet, okay? Third ingredient, the algorithm. Very simple. It's called self-supervised learning, and it's done via backpropagation. This is what is called the next token prediction. Probably you have heard about it. And it's nothing more but applying the chain rule, so the backpropagation algorithm, to the weights of this neural network, such that the error for the tokens, so the error of the prediction, is minimized. And you do this for a lot of times with the NVIDIA GPUs or whatever. And then the fourth ingredient is this fine-tuning. So after all this big pre-training has finished, the researchers take a very curated set of data, and they give this to the model, so the model learns to output the responses in the way the users like, right? So these are the ingredients. They have led to this revolution that is almost at the beginning, and they trigger this natural question, right? Are these predictive models stochastic parrots, or are they primitive reasoners? Is there some kind of emergence happening there? It's a hot debate. It's open. The concept of stochastic parrots was coined by Emily Bender, I think. And then there is this paper from after the ChatGPT 4 that claim that there were some sparks of general intelligence. We have this interesting paper from people from Santa Fe Institute, Melanie Mitchell and the director, discussing this. I recommend this, and also the recent work of Apple, the illusion of thinking. My point here is that this issue is not solved. It's not clear. We have evidence against it, okay? And we all have experienced them, at least if we have used these models. So evidence for this, we have this empirical scaling laws that basically says that the models are getting better and better as we give them more data, more compute, and so on, right? So since 3 years when ChatGPT arrived to now, these models have got a bit better. On the other side, we also have these personal experiences that tell us that there is something weird with these models. No? They don't have this common sense. For instance, you ask them for a random number between 1 and 50, and all of these models give you 27, which is they are like collapsing to the same attractor. Or if you try to put the clock hands somewhere else, they will not let you. They will show you the same 10-10 all the time. So what is happening here? I want to ask the audience just two questions because I'm intrigued. The first one is how many of you use these kind of models in a daily basis or often? Yes. Okay, yeah. I was expecting this. And the second question is, how many, I know the question may be a bit vague, but how many of you think they are just stochastic parrots, let's say? Okay. Yeah, I was expecting even more meat of this because I kind of agree with this idea. But yes, sorry.
What is the definition of this?
Yeah, now it's the one important issue is how to define these things, right? That's why I say that this question is a bit vague. Okay, so it was tricky to ask this, but let's wait a bit. So, because my point is that maybe this question is irrelevant. Why? Because of this. Now there is this second axis. Okay, it's called test time compute. Let me show you with a video what test time compute means. Okay, I think that the audio is on. Okay, you get the idea, right? Basically, these engineers, they let predictive models, they allow them to think. So now they reason at inference time. So you give them the problem, and they spend some time before they give you the answer. You can do this with two kind of methods. The first one is simpler. It's what's called the chain of thought. So it's the trick of the model outputs these tokens that are thinking tokens, and they think for a while and give the answer. But now things got a bit more refined, and we have the reinforced learning with rewards, or the group relative policy optimization. That is the algorithm that made DeepSeek famous. And basically, what you have here is if you can evaluate the quality of your response, then you can reinforce learning on this. And what these people do is like the idea of the infinite monkey theorem. You just throw a branch of futures, and at some point they will write the Quixote. Okay. But these are not monkeys, these are stochastic parrots, quite clever. So basically, in my opinion, they will crack a lot of problems just by this brute force approach. For instance, we have, with this strategy, they went from solving games with very clear reward function like chess, Go, or whatever, to protein folding, now to explaining the genome, and even discovering solutions for algorithms of matrix multiplication, and so on. It's crazy, okay? So the question is that all? This paradigm, brute force, large pre-training, so compressing the whole internet, plus reasoning time in this capitalist world where we live, will lead to maybe most problems with economic value being solved by scaling these two axes. But limitations and risks. There are many, but since these are A companies involved in the system, they don't care. They are there for the profit. But the limitations are here. I'm not talking about the risks, which are also important. Some limitations that I want to mention. First one, out of distribution generalization. Current models cannot think out of the box of the training data, by definition. They are interpolators of these distributions of the data. They cannot learn without tons of data and then rewards. They need billions of examples for solving some tasks. They struggle with efficiency. So current approach is energetically huge and absurd. They pretend to spend like the whole GDP of the US to train these systems. I mean, there is a lack of elegance, because simulating intelligence by reading all the text we have written and then thinking for an arbitrarily large time, maybe it's not that surprising at all. I mean, yeah. And more important, there is overwhelming evidence of better alternatives, right? So nature has discovered very different mechanisms. Let me tell you about the intuition shortcut, or how I understand this. To understand this shortcut, let me give you an analogy about chess. So we have this tournament in Norway, the 2025, where Magnus Carlsen, the GOAT, so the greatest player of all time chess, top ranked, playing against the current world champion, Gukesh Domarajo. And it's interesting because there is a bit of beef in this. So Magnus, on an interview before the tournament, he said about Gukesh, Gukesh is still a bit of a mystery to me. It's weird because you have somebody who is like so much better at classical chess than he is at rapid blitz. you can tell that this guy, when he plays, he does not have the intuition to play good moves quickly, but he calculates unbelievably well. In classical, it works quite well, but you see it in certain games that he just makes very strange positional decisions because he doesn't have the same positional filter. This is the idea, okay? So even more viv, writing in Twitter, you come at the king, you best not miss. So the game was played 11th June, I think. Do you want to know what happened in that game? Right, no? Let me show you. This is the final moves. Okay, yeah, so Magnus slapped the table, he was upset, he lost, okay? So in that example, brute force won. The same analogy we have now in the AI ecosystem. Is there hope? I say yes, and the answer always is given by physics. But what kind of physics, okay? What kind of physics? Let me introduce you a paper. Yes.
I don't understand what. So
Okay.
I mean, what is the problem?
Yes.
That you're addressing from the previous transparency, and what do you want to go exactly?
The problem is that, well, there are different routes to reach like intelligent behavior. And I'm claiming that the current paradigm is following a very brute force approach to solve this problem. And I'm proposing now an alternative that is coming from physics. Okay?
Because brute force is
It's-
good enough.
Yes, exactly. I hope it's not good enough for you either. Okay.
Well, practice makes perfection, right? So
Yeah, I mean, I'm
what we do has to do.
I know we need brute force. We need to practice. But as a physicist, we want to isolate the mechanisms. So what I did, and I will explain now, is going to a limit where you don't need to practice. Let's see, where you don't need brute force, and let's see if something emerges there. Let me go into the details and maybe things get clear. I just wanted to give this context. I know it's a bit controversial, the topic, or a bit esoteric, but that's my point. I want to make it concrete and physical, okay? So I'm trying to solve this with physics. What physics? A bit weird physics, okay? Causal entropic forces. This paper, I discovered it 10 years ago when I was doing my master. It's published in PRL by Wisner, Gross, and Freer. And the question these people try to answer is the following. What happens when you apply causal entropic forces to the degrees of freedom of a mechanical system that is coupled to some environment? Okay, let me explain what this means. A causal entropic force is just a force that it goes in the direction of the gradient of this entropy, and this entropy is not the usual entropy, but of our configurations, but an entropy over future paths of the system. So it's an entropy where configurations are paths. You can compute this in these mechanical systems these people use, like particles in a box or whatever, and actually define a force that is applied to the degrees of freedom. So it can move the particles or whatever. And what is a very abstract idea. And you compute these entropies of path up to a tau horizon, so up to some future, okay, in the system. Then they show that simple mechanical systems, when this force is applied to them, they show complex emergent behavior. For instance, a simple case is a particle is moving to the center of the box, or this inverted pendulum that after this force is applied, it will invert and stay there, or more complex behaviors like tool usage or social cooperation. But this is like a curiosity. Yes, Paulo. Yes.
The direction where it have more different paths.
Available. Yes, exactly. See, this is the idea. So, for instance, in the box, and the system has also thermal fluctuations. Yes, actually, you need this stochasticity because otherwise the system would be deterministic to the future, and then you need some noise to actually create this cone of futures. And it's an ad hoc force. It's a force that you assume that it's pushing the system towards states that maximize the future. This is the idea. Yes, Fernando.
It's capital X because in the definition of the entropy, you only
Good-
have
good point.
one
Good-
basis
Yeah.
on the right-hand side.
Yeah, the question, capital X is like the macro state of this system, which here is not, it consists of the present, so it's like the system at at each present and all the cones of trajectories. So the x, which is defined by x0, so the initial state, it represents the cone of the futures. But you will understand this better in my explicit example, I hope. But it's still difficult to understand. I think it's more of a curiosity because it's, of course, intelligent doesn't happen like this. You don't invent this force, put it in the degrees of freedom of particles and weight, no? But the idea is interesting. That's my point. I forgot about this, did my thesis, then all this revolution, and came back to the idea, and I saw that there are some related ideas in the machine learning community and theoretical neuroscience that are somehow similar to this. No? And for instance, the maximum entropy reinforcement learning, where you put the agents to play in the environment, and you give the reward from you define some reward, but you have also to maximize this entropy. There are frameworks that don't use rewards, so they try to explain this intelligence how without rewards, intrinsic motivation, empowerment, maximum occupancy principle, more theoretical constructs, the free energy principle, whatever. But they are complicated. They are putting more models to the system. They are not isolating what is happening there. But people start to see it. There is this preprint in arXiv, but Kiefer this very recent this year that shows that all these frameworks, intrinsic motivation, can be seen as constrained entropy maximization. So the problem can be seen as basically entropy subject to constraints. And this leads us to Edwin Thompson-Jaynes, okay? Jaynes. And the principle of maximal caliber. It says, the principle of maximum caliber, or maximum path entropy principle, can be considered as a generalization of the principle of maximum entropy. It postulates that the most unbiased probability distribution of paths is the one that maximizes their Shannon entropy. This entropy of path is something sometimes called the caliber of the system and is given by the path integral, the same path integral that we saw before. Okay, this is maybe a bit abstract yet because it's about trajectories, but this is what Jaynes did already with statistical mechanics, equilibrium. So he showed in a previous paper, even more famous, that you can derive whole statistical mechanics as a process of statistical inference. So you don't need physics, you only need information theory and constraints from the world. And he wrote in this article, it is now evident how to solve our problem. In making inferences on the basis of partial information, we must use that probability distribution which has maximum entropy subject to whatever is known. This is the only unbiased assignment we can make. To use any other would amount to arbitrary assumption of information, which by hypothesis we do not have. So the idea from this slide is, when your microstates are configurations, you use maximum entropy principle, right? When your microstates are trajectories, what you have to do is use the maximum caliber principle. That's the idea. But this is not what is happening in machine learning now. So the question is, what is the minimal, the less biased way to encode this principle, like a principle we take as truth, into a learning model? And here is the key idea that I want you to understand, and the framework I'm showing now. And it's just connecting the evidence I show now. So on one hand, we have these super huge, powerful large language models, which are nothing but probability distributions that predict the data, so the probability distributions of the underlying data generated process. But we know that these super powerful systems, they violate this principle, right? Because they are just predicting the data, but they are not maximizing their entropy. So what is an easy way to actually impose this principle in the system? To apply the causal entropic force. Where? To the degrees of freedom of this system. The degrees of freedom of the neural network are the weights. So you apply a force to the weights. Learning is also a force that is applied to the weights. So this is the same. So now we are ready to introduce my framework, which I call mind tuning. Very general setup, okay? Data. We have discrete sequences, which are trajectories, and they represent the observations we have from the world. They can be tokens, what they use in ChatGPT, they can be images, they can be states, actions that what people use in reinforcement learning, sequences of data in time, okay? Second ingredient, you need a policy. You need a model for the decision making. Yes, and we use neural network. Okay, so neural network is a model that will produce a decision based on this data. So a neural network gives an input, it takes an input, gives an output, which is called the logit, and has parameters theta. And then people use this softmax function to actually translate these logits into probabilities, which makes the decision, right? Be careful because, or a warning here is that this beta in the softmax is what people used to call temperature. Like this thing you can tune like the temperature of the output, but this is not a temperature for me, at least. This controls the greediness of the policy, how deterministic the policy is. But the idea is data and policy. And of course, you need to define an objective function. What is going the model to learn? Where we find the parameters. And the objective function I propose is very simple and is the original objective function of transformers or this predictive model balanced by this causal entropic term. So it's an instance of the exploration trade-off. Very simple in the context of predictive models. So the first term, this CE, and of course the objective is to find the parameters theta that minimize this function. And we do this via gradient descent, but this is not important. Important thing is that this function has two terms. The first term, the cross entropy, is what is known as the next token prediction term, also called perplexity, negative log likelihood, error minimization. It can be seen as an energy, and systems want to minimize this. We want to minimize this error. You can put is the Kullback-Leibler divergence between the distribution of the data and the models and average it over the data points. This is standard. And the second term is very simple and is based on this idea of causal entropy. But what kind of path entropy? So the entropy of the paths generated by the model itself. That's the key idea. So if you don't want to put the model to interact in the environment, you can still compute this entropy of path. And you can do it with the models itself, self-consistently. So the model, once it's trained, can generate futures, and you can measure this entropy there. I call this imagination, or it's a metaphor for imagination. And you can see it's an entropy over future paths. Okay, still it was very abstract. Let me introduce you the maze, finally, right? So the maze, I see it as an abstraction of a reasoning task. Because let me ask you first, see this image, like a maze inside an empty space, and I ask you, what is the task here? Anyone there's to answer? Yes?
Wow.
Yes, so escape the maze, right? But this is one task. This is the data, but there is also another task before. So you have to learn the maze to find the good exit, because you have to learn what is the map of your problem, right? You have to learn the physics of the wall. And then, yes, the solution of this problem is to find the exit, find the escape of the maze. But there is also the learning, right? So to model this, what I use is data that consists of trajectories that are just random walks that explore this maze, okay? This is good for two things. First thing is that the random walks respect the physics of the maze, so they are exploring this maze, and if you have enough trajectories, in principle, you get the shape of the map just from these trajectories. And the second interesting thing of this data is that random walks are not intelligent, so they don't find the solution that Pablo was saying of escaping as fast as possible. But they represent compatible physics of the world, so observations of physics, but they are not intelligent and they don't have reward. Important concept, yes.
Generalized how to
No.
get out of the maze of it. Just you put it in the rules, right? So it's not going to.
It's about learning the rules, because now here you see the maze, but what the model actually sees during learning, it's just trajectories. So from the trajectories, he has to learn the rules. He has to learn what kind of transitions are not allowed. So it's implicit, but you could also give the whole maze, but this is more tricky and more interesting. The maze is also interesting because, similar to what Mo said, you can play with the with the difficulty of the problem. So for instance, changing the data representation, you can go from a Markovian problem to a non-Markovian problem. For instance, what I mean with this is if your data, so if the representation is the whole maze, then you don't need to know that you don't need the history of the past. The decision is based on where you are. You decide where to go. This is the same with chess. Chess is also Markovian. You see the board and you make a decision. But if the information is not complete, so if you only have partial information, like the sequence of moves, then the problem becomes non-Markovian. But this also complicates things. We can stay in the Markovian setting, where we can use a very simple neural network. And we stay also in a small state space, so small grids. In this way, we can calculate analytically this causal entropy, because you can actually do it with Markov systems. So this is the idea. We have this objective function. We train them. Let's do some experiments. So I will show some results of the model for different values of this temperature. Okay. So for lambda 0, no temperature, so only next token prediction. Of course, the model at inference is doing a similar pattern, the one it's observing the data. It will respect the physics. It will perform constrained random walks without escaping. If you increase too much this lambda, and I call this imitation phase, but then you get to the hallucination phase. And the model is trying to maximize entropy, right, of paths, and he's doing it by basically breaking the rules, so jumping over the walls. And the interesting part is, of course, that there is in between another strategy that at the same time maximizes the future paths while respecting the constraints. And this strategy or phase is what I'll call the intuition phase, and you get models that do this, okay? They just escape the maze. It's very proof of concept of this mechanism.
What it was?
The CE, it rewards that you stay close to the data. So the question was, what this term is rewarding? Data. Exactly. Yes. Maximize future paths. So this second term, yeah, the one that comes from data is this. Exactly. Yes. That's the proof of concept. In the maze, maximizing future paths while respecting constraints leads to this solution. But this is like the solution that the system has, but it's a metaphor, because a maze is an abstraction of more complex problems. Yes. It's a very good question. So how to fix lambda? Here, we are not fixing it. So we are just setting one lambda at the beginning, and let's see where the system ends up. But later we will explore this because it's very important, right? So connecting to Pablo's question, we have the data trajectory, and then we have the model trajectories with this mechanism, I propose. They are very different. They deviate from the data in the way we want. Well, let's say, what is this? I started thinking about intuition. I like this metaphorical concept. I was looking for the definitions of this intuition. It's very vague how it's defined, because this concept of psychologists and philosophers, right? I like the definition that ChatGPT gave me, and it's, how do you define intuition? Knowing something without knowing how you know. Okay, well, or the Wikipedia says the ability to acquire knowledge without recourse to conscious reasoning or needing an explanation. But it's vague. They use gut feelings, inner sensing, inner insight. Yeah. So what I prefer to do is build an operational definition of intuition from what I observe. And I propose, yes.
I mean, it's not intuition, right? I mean, intuition, I would say, is a reflex. It's something.
Yeah.
This is not what it's doing here. What it's doing here is basically well, there is a wall, but maybe there is not a wall, and then you try something different, which I think imagination probably is more appropriate.
Imagination. So the question here is that maybe intuition is not the good word for this, and maybe imagination is better. I would like to make the distinction. So imagination is the process that you do during learning, and intuition, what I call, is the the behavior of the system at inference. Intuition is something that you do fast without thinking, and it's not in the data. And that's what I hear. Let me give you the definition I propose for intuition. So an spontaneous, intelligent behavior that maximizes future path entropy while respecting constraints. It is not fully explainable from the training data and emerges when learning occurs at the critical balance between prediction and imagination, without explicit goals, rewards, or requiring interaction with the environment.
You can find
Yeah,
intuition the way you want. The question
Yeah.
is whether you tell somebody the definition, whether when it comes to your mind is intuition or not, right?
you can say that maybe intuition is not a very precise concept. I use this term to define the operative regime I observe. You could call it something else. But let me now justify this claim, okay? So let me show you the phase diagrams. So you will see two phase diagrams, one for the genotype, which is the internal properties like the cross entropy of the path, the causal path entropy, these two terms. And also we have a phase diagram for the phenotypes, so for the behavior. What you will see is things occur for the mean first passage time, so the time it takes the agent to escape the maze, wall hit ratio, so how many errors you make, and the intuition phase. So let's see. Top plot as a function of lambda, you see that the cross entropy, so the energy remains low until some lambda, where it abruptly jumps, right? But the entropy, it stays low and then increase much before than the energy. And then this leads to this window here where you can have actually low energy, but high entropy. And you can see in the fluctuations, because this is for different realizations, that so the heat capacity, so the fluctuations of the energy peak at this region, but the peak of the fluctuations occurs earlier here. Whatever. Let's go now to the second diagram. So for the behavior, and you can see that this region here coincides with the region where intuition emerges. So this means a region where you have low mean first passage time and still zero errors. If you increase too much lambda, then this window closes and you start getting errors. But you can see from this black curve that there is something weird happening here. And this is the new phase that is emerging from this trade-off. Yes, Pablo. With this likelihood here, this is because I'm running different realizations with different initial conditions and just measuring the fraction of these experiments that end up with the system producing it. So the point of this not being 1 or 0 is that is stochastic. It depends on the initial conditions to end up in this state. Well, you can see just from these points here. Some solutions get at the same time this, but it's just a proxy of the other two to simplify visualization. This is the behavior of the intuition phase. The intuition phase is like the set of weights that generate. So the system reaches a set of parameters that produces this intuitive strategy. But here, for instance, after the intuition window, you see another region. This is, you can forget about this. But I ran the experiment many times, and I see that only for a fraction of these experiments, you reach. So there are some experiments for some lambdas that fall into this behavior, but not all of them. The behavior I define it from the maze. So behavior is basically having a mean first passage time that is the minimum time to escape the maze. So here it would be 1, 2, 3, 4, 5, 6, 7, 10 steps, and you have to have 0 error. So basically, intuition phase for that maze is when the time goes below 10, and it's just
leaving the maze in the minimum time without
exactly. But okay, this is the idea. Yes. The initial weights are sampled random from uniform distribution of weights in this case. So some questions and almost done, because these are some effects you can ask to the system. How far into the futures should the model foresee so that this likelihood for the intuition appears? So how long should be the future horizon? Here you will see the phase diagrams for different horizons. So horizon tau 1, only one step into the future, 20 steps and 40 steps. The message here is that the intuition phase only appears for sufficiently long future horizons when the model discovers that escaping the maze ASAP allows it to gain more causal entropy in the long term while respecting constraints. However, if for intermediate future horizons, a cheating phase emerges. This is the model discovering that there is an easy way to escape the maze fast by slightly deviating from the data. But this is like vice before virtue. It's like finding the escape, but not through the correct way, but from another corridor where you only need to break one jump. So it's like cheating, because cheating is always more tempting than finding the good solution. And of course, if you go to only one step, this phase disappears and you move from imitation to hallucination. You need 4AC ability. Another question similar is how capable, so the size of the system, is it a true phase transition or not? How capable does the neural network need to be? How many parameters you need to learn this phase? So the same, different capacities, and the idea is the same. The intuition phase only appears for sufficiently large capacity when the model is able to spontaneously encode a sophisticated mixed strategy from this tension of path entropy and error prediction. And I don't show this here, but if the model becomes even too large compared to the problem it's trying to solve and the available data, then it's like trying to kill a fly with a nuke. And then you get overfitting problems, and then this window can also get smaller, but it's a thing I didn't explore. Another effect is, of course, the effect of the difficulty, no? How does the complexity of the problem affects this intuition phase? The same, again, very intuitive idea. So the more complex the problem becomes, the more difficult it is to find it, right? So in a corridor maze where you have only one corridor, the optimal strategy is very similar to data, and the intuitive window is very large. As you make the maze more complex, intuition is harder to find with this likelihood idea. And in some mazes, for instance, this room with just one exit, this system don't find intuition here. But, and this connects to the question you asked in the first row, how we can maximize this likelihood of getting this phase, no? And we can do how can we get to this intuitive phase easily? And we can do this with protocols. So changing some parameters during this process. I just present the protocol of changing temperature. So you simulated annealing, or when you increase temperature in physics or whatever. So here is the results for the experiments I showed before. So the same kind of curves. Here I also show the curve for the mean weight of the model. You can see that there is also this kind of two regimes. And here is the same I showed before. So the behavior, the mean first passage time, and the wall hit ratio, but depending also on the greediness, so for different stochasticity. But basically the idea is that we want here a region that is blue, has blue, so low time and low error. And we don't get this here easy, it's not get. But we can get this by doing what is called a diabatic protocol, right? So in the diabatic protocol, you start with low temperature, and you smoothly increase the temperature, right? You let the system stabilize and so on. And when you go to very high temperature, then you start decreasing again. And what we see here, what I see is that there is hysteresis, so path-dependent trajectories. And the important thing is, so this points to multi-stability and to, yes, non-stationarity and this kind of stuff. And the key ideas is that when the model starts learning via pure imitation, so first lambda 0 and copying the wall, and then increases lambda adiabatically, then the intuition phase is much more likely to be found. And this is what we observe here, that you actually see the region of blue and blue. So finally, we got there. But when the model starts learning with lambda large, so already at the beginning having high temperature, and then you decrease lambda adiabatically, then this intuition phase is much less likely to be found. And this makes sense also to humans. You have, when you are born or whatever, you have to start first learning about the world, imitating it. Only when you have a good world model, then you can imagine futures to get to leverage this and find something else. Yeah.
The reason is the first response.
Yes.
No, right? It's how you.
But intuition so intuition for me is the behavior that you observe. But for me, it comes after you are learning in the right way. It's like reading a book. If you are stupid, you don't know anything about the world, you memorize, for instance, for an exam, you get a math textbook, you start reading it. The way that this mechanism works to encode intuition in the weights is, yes, you keep reading the book, you memorize the book, but you keep asking, what if, what if, what if? This is a natural way for me to learn things. This is when this mechanism, you learn, so yet, but this is a very important, but this is my point. So intuition is a behavior that you have to learn how to do it. This is the point, yeah.
Could you go back to so I really like the idea, but for example, I mean, of course, it makes sense that this is the first example. But for example, here you have the space out of the labyrinth, which depending on the size you fit it,
Yeah.
is going to probably give a bigger drift. Well, it will depend on how, but you will give a bigger drift or not. So how do you think, for example, this paradigm of linear learning will translate, for example, to a space where the trajectories have, for example, generating an image, no, a black and white image with 3 darkness scales. So in that way, you have, the number of pixels is fixed, the pixel scales are fixed, and you don't have any possibility of this outside configuration space of influence. How do you think this would translate?
Yeah, good question. The question is how this maximization of entropy translate to spaces that are not so obvious, no? Because here the space on where the trajectories operate is the geometric space, and you can actually maximizing causal entropy in that space leads to this behavior. What is the space of futures of images or whatever? I don't know, but maybe the idea is always the same. You need to identify the correct space, maybe it's a latent space or whatever, and maximize futures there, maybe also for images. But I don't know. But here, in this particular case, you don't observe intuition because the data is very low. So few trajectories from the data escape the maze. So it's very difficult from the model to learn that there is an outer space outside where it's good to go.
Also, there is not so much difference between the outside and inside.
Exactly, that's also another experiment. I did it. If you change this maze, because these are periodic boundary conditions, and keep making bigger, at some point the maze, so the space inside this room will be larger than the space outside of the room. And the model pretends to stay there. But yeah, this is the tricky part. So the problem defines the complexity of this and how difficult it is to get this. So there are different mechanisms. There is also an analytical explanation. I don't have much time, but so the challenge is that this is a very high-dimensional system with nonlinear dynamics. So how do we handle this? We need to think and find symmetries and suitable order parameters, and that's what I did. My solution is you can find an effective low-dimensional description using a suitable order parameter, and if you do so, then you get an analytical policy that can be evaluated without paying the cost. So it's basically analytical. And this theory is based on the idea of defining a scalar rationality parameter, M, that measures the rationality of the agent. So from 0, it's random, to 1, that is completely optimal. So I'm building this after the experiment, so I know what I want to get. I want a solution that can reproduce the solutions I observed and then put it back in the loss function and see what it means. No? So with this idea of this parameter and then assuming a Boltzmann policy, which also resembles the policies of the models, with this beta, and then defining 3 types of costs. So basically in these problems, like in a maze or a chess or whatever, you have in the decision you have one good, so the good direction, optimal move, some realistic moves, and some non-realistic moves. That's basically the three kind of choices there are. So tuning these costs using this parameter and plugging in the policy, and then plugging all this into the free energy or this functional, which is analytical, then you can see what happens, right? And what I see is that this theory qualitatively reproduces experimental results and confirms these rich phase diagrams. So we have this entropy-driven transition, the energy one, these three regimes that we observe in the experiments. You have to tune the parameters a bit, but the idea, and also we get this phase diagram for the stability of the best solution. And you see from this idea of the adiabatic protocol and so on. So for low lambda, you have only one solution. Then on some lambda, this solution changes and becomes with positive m, larger m. So this is where the good solution is already. Here is completely stable and the unique one. But then at some point, the global solution is the bad one. So one that has a very low m emerges. And this is the one of breaking the walls. So you see this window here where you have multi-stability and so on. And just another interpretation to understand this framework from Bayes. So the question is, can we cast this mind tuning as a Bayesian inference? Bayes rule, no? So you update, so you start with a prior of your beliefs, here the model. You update this prior with the data and the likelihood that this data is explained by your prior, and you get a posterior, no? So updated beliefs. Actually, you can, from the definitions of the terms, you can write mind tuning as this. And the idea is, in mind tuning, the prior is the entropic prior. So it favors models that generate diverse and plausible futures. It's a very optimistic prior, okay? So the model filters this optimistic prior. Well, it's not optimistic per se, it's what physics says, maximum caliber. So you have this optimistic prior and you filter it with the realistic, you become more realistic over time. However, in a standard next token prediction, the prior is flat. They don't impose this prior. So all the futures are equally likely. The model is just enriched by the data, but it doesn't have this incentive to generalize. It's like the other way around. It's very pessimistic and just get more optimistic, but it should be the other. And actually, in practice, what I find is that you need a hybrid strategy. So as I said, you need this prior at the beginning to be constant. So you start just imitating, and then you change your prior, and you become more optimistic. That's how intuition is betterly found. I'm finishing just some implications of this in the context of large language models if this method scales, okay? So we have this first scaling axis. So from this framework, we can see that current models are trained in the frozen phase. So lambda 0 or this constant prior, right? So what my framework or this framework predicts is that out of distribution generalization is not possible only by imitation, as we show in the maze, right? But there are two caveats to this. They are very concerning. The first one is that human data is already of high quality, right? Which implicitly maximizes some future path diversity subject to constraints. These models are parasitizing our efforts as humans. We created a very intelligent data and they are imitating it, right? The consequence is that they will be an intelligent simulator that will be indistinguishable from a genuine one, because the data is intelligent already. So, but the maze shows that they can. So in the maze, you put ChatGPT and it will not show the strategy that's emerging. It will copy the strategy of the data. The second caveat is that even if this is not true, they have this second scaling axis, right? So besides scaling data, now the model reasons. And this brute force intelligent simulator can solve many problems. And this, I call it the infinite parrot theorem. It's also very scary. But physics taught us that these systems are violating the maximum caliber principle because they don't explicitly maximize path entropy subject to constraints. They are missing the entropic prior. As Homer Simpson said, in this house, we obey the laws of thermodynamics, right? So if we do this, and we impose the maximum caliber principle, then mind tuning discovers this intuitive shortcut that emerges by learning at the critical balance and between memorizing what is and wondering what could be. This suggests that there is a third axis of learning. And this is this imagination, and it's necessary to explore this to actually encode the intuition in the model. Okay, just to conclude the second chess analogy, it's about this book that written by the Austrian writer Stefan Zweig. In English, it's called The Royal Game, and it's about a guy, the main character, that is imprisoned by the Nazis during 2 decades in a room, in a cell, and the only thing he has is a book of 50 games of chess that are very famous. No, he doesn't know anything about games or chess. He doesn't have a board. He only has this book. So what he does to kill time is just reading this book, memorizing first the 50 games, and then for boredom he starts imagining he's playing against himself. Right? So let me read this just to conclude. So really, you mustn't expect too much. So I'm sorry. And so he learned chess by this, and the final scene of the book is this guy, our main character, is playing a game against the world champion of chess in this world. And before the game, he says, really, you mustn't expect too much. It will be nothing but a test for me, a test whether I'm at all capable of dealing with chess in a normal way in a game with a real board, with substantial chessmen and a living opponent. For now, I doubt more than ever that those hundreds, they might have been thousands of games that I played, were real games according to the rules, and not merely a sort of dream chess, fever chess, a delirium in which, as always in dreams, one skips immediate steps. Surely you do not seriously believe that I would measure myself against a champion, blah, blah, blah. What interests and fascinates me is nothing but the human curiosity to discover whether what went on in myself was chess or madness, whether I was at the dangerous brink or already beyond it. That's all, nothing else. So yes, there is at least literally evidence, okay? So the main character of this book learned to play chess via mind tuning. This means memorization plus imagination of future paths following the learned rules without interaction with the environment at the edge of hallucination. You want to know what happened in the game, in the book? So they played 2 matches. The first match was won by our hero. So yes, you can learn how to play chess with mind tuning. But then he got very excited, accepted the rematch, and in the second game, he got completely nuts, started doing checks where it's not possible. So it got mental. So be careful with the strategy because it happens at the edge of hallucination. So yes, a summary, what I said, this intuition phase that is discovered with this mechanism is the outcome of learning intuition. It's a critical phenomenon that requires sufficiently model capacity, sufficient horizon, and good enough data, depending on the problem, to emerge. And the learning process shows strong hysteresis. History matters, okay? So intuition is more reliable found by learning the rules of the world before learning to imagine what I said. And this mechanism is confirmed by an unsolvable effective model that reproduces the findings. So challenges, the big question is, of course, will this mechanism scale? Because we tested in a very minimal sandbox. This means translating it to physical control problems like the inverted pole, to strategic planning. I basically want to try this in chess, and let's see if the little model can actually encode this intuition, or to more abstract reasoning tasks, like these challenges that are basically the only benchmarks that these models cannot solve yet. And we humans can solve them. For this future, I expect 2 lines. And I'm looking forward to collaborate with people because they are going to be quite difficult. And the theoretical line is to develop this framework, a rigorous one, to prove the phase transitions, if there are universality classes to put these transitions, if you can find exact solutions beyond the 2-dimensional maze. This is necessary because what I show is that these optimal protocols of increasing temperature might be very tricky to find. Maybe we need a theoretical solution for this, okay? The second line is more computational, and it's related to developing clever sampling strategies for this causal path entropy estimation in high-dimensional spaces. You cannot do this analytically anymore, and it's very difficult to sample because of the combinatorial explosion of futures. We need clever algorithms, maybe quantum, maybe, I don't know. And I think it's a high-risk, high-reward endeavor, but yeah, very excited about this. So thank you. That was all.